Okay, what's up, everybody? I got Jason here with me,
What's
and
up?
oops. Um, so there's a space audits video that we pulled clips from in our last video, and I figured, we could probably go over the video a little bit more in depth to hear like what, the context of everything. Like we did get a comment from the Ether cosmology. I thought it was Alan or Shane, but apparently there's like a Czech guy or something that, or Spanish speaking. I don't know where he's from. But anyways, he that channel commented saying that we don't understand kinematics and this and that, but then never responded to specifics on his comment. So we figured it makes sense to make a video and actually break it down, go through the claims that they make and respond. And yeah, is there anything that you wanted to add before I start playing the
No,
claims?
that's a good introduction to go off of.
Okay, cool. All right, I'll just get right into it then. Here we go.
Upward accelerating, or is the Earth stationary and there's a downward vector caused by some unknown force, right? To provide the acceleration that we see when the objects fall. Now, it could be an illusion. The objects could have relative deceleration to an upward acceleration that's constant, or the Earth can be stationary and the object could just be falling to the ground. Now, physics is broken into two major parts: kinematics and dynamics. Kinematics means measurement and prediction of motion without regard for causal mechanism. The equations that govern kinematics are strictly acceleration, the x-coordinate, and constant acceleration, so velocity. So what they're doing is you're just making future predictions of motion based on the information that you have on the system right now. For example, someone throws a ball at you, you're immediately calculating its trajectory, its speed and time. You're not concerned with how much air friction there is, how much resistance the ball is experiencing as it's traveling towards you. None of those factors are what's being accounted for. That section of the calculation is called dynamics, when you introduce actual forces to make predictions of future motion, right? So if you're like, how far can I throw that baseball, right? Based on its weight, based on how much force I'm putting into the throw, based on how much wind resistance or air resistance there is, or whatever media it's going through, there's going to be friction there. So you can account for all those things, and then when you get into the dynamic analysis of a system, you then have to choose like what forces are you going to account for, what's going to be negligible, et cetera, right? So when you get into that sort of analysis, it changes the nature of it, right?
You
But
pause it there.
distinctly two separate.
Okay. He's absolutely correct in his definitions for kinematics and dynamics. Kinematics being measurements optically of motions and relative motions without any causal mechanism or any forces applied to anything. And then when he goes into dynamics, he wants to say, then we've got to choose what forces to account for. When in the very first instance, all we have a first order measurement of is a force, and that is with an accelerometer, a proper acceleration measured from the ground. So we have our dynamic force, our proper acceleration, an actual direct first order measurement of a force. So he denies that force and wants to choose a force of a optical measurement of distance over time of something falling, which there are no forces measured on anything falling. So right there, he completely flips the dynamics and kinematics and tries to put that we're not taking into account any dynamics whenever that's exactly what he's doing. He's not taking any of the forces into account. He's just prescribing a force to something that's not actually measured. It's just an optical kinematic measurement, and then they're making up a force of downward acceleration, which is not measured. It's
Which is the
just
same thing.
optically interpreted.
It's the same thing that the gravity people do, that the spendy base time people do, or they,
The Benny space time. Yeah,
yeah,
exactly.
it's literally the same thing. So I don't know how he doesn't see that, like the correlation there, that they're both making something up that isn't measured, that isn't there. So not to say that electromagnetism doesn't exist, but just claim that that's the reason why all objects fall. Like you have to back that up with something. You can't just
Right.
say that.
Right. There's two different types of acceleration. There's a proper acceleration, which is an actual acceleration that's measured with an accelerometer in the spring scale or any kind of actual measuring device. It's not just a distance over time type measurement. It's an actual direct first order measurement.
Should I
And
play
then,
the proper?
well, yeah, hold on.
Okay.
Yeah, and I was gonna say there's a coordinate acceleration that is completely optical, that is just relative motion, something changing velocity over time, which would be a coordinate acceleration, in reference to a coordinate system, acceleration in relation to a coordinate system without any forces, actual forces measured.
Got it. So, and we found this little short video on, like, describing that with visuals and stuff. So maybe I should play that now, or should I wait for that?
No, yeah, no, that's a good one.
Okay, cool.
Now that we've stated the equivalence principle, let's see how gravity is different from the other forces. To do this, we're going to have to turn the equivalence principle into real mathematics, so that we can do calculations that involve both gravity and relativity. And to do this, we'll introduce the concept of proper acceleration, which is measured by an accelerometer. If you're inside a car and the driver steps down hard on the gas pedal, causing acceleration, you will feel as if you're being pulled towards the back of the car. This feeling of being pulled backwards is your body feeling proper acceleration. So proper acceleration alpha is the acceleration measured by an observer in their own reference frame relative to an inertial reference frame, and proper acceleration is measured with an accelerometer. An accelerometer is made of a rigid outer box, with an inner ball that is electrically and magnetically neutral. The ball is balanced on springs that are attached to the outer rigid box. The spring compression is what helps us measure alpha. The larger the spring compression, the larger the proper acceleration felt by the accelerometer, in some examples. Let's say that we're in deep space and there is a rope that is attached to an accelerometer. If the rope pulls the accelerometer forward with constant force, then the outer rigid box will get pulled forward, but the inner ball will lag behind, until it is pushed forward by the spring. This results in the spring compressing. Since one of the springs is compressed, the accelerometer measures a non-zero proper acceleration alpha. Because the ball pushes up against the spring, the accelerometer can tell it is now in a non-inertial reference frame, caused by the force of the rope pulling on it. Now, if we have an accelerometer where the outer box is made of iron, it will get pulled toward this magnet. Now remember, the inner ball of an accelerometer is always electrically and magnetically neutral, so it will not feel attracted towards the magnet. Once again, the outer box will get pulled forward, but the inner ball will lag behind, causing spring compression. So once again, non-zero proper acceleration is measured. If the outer box has a rocket attached to it, which applies a force, as the box gets forced forward, the inner ball will again lag behind, causing spring compression, and so we measure a non-zero alpha. Now, what about the case of an accelerometer moving in free fall towards the Earth? Since both the outer box and the inner ball will have the same acceleration relative to the Earth's center, this means that the inner ball will travel with the exact same motion as the outer box, meaning there is no spring compression, and therefore proper acceleration alpha is measured to be 0. We can see here that gravity is different than other forces in nature that we've seen, because gravity acts on both the outer box and the inner ball equally.
Gravity, aka ether, whatever you want to call it, like it's literally the same thing in my
Right.
opinion.
They have to come up with a like you said, it's different than any other force. Like it's never like it cannot be demonstrated in any other way. In my world, this is the unicorn fart because
Yeah.
it is it can't be demonstrated. It's a force that can act on different states of matter, different masses, all equally to where they all coordinate accelerate at the same exact rate. There is no proper acceleration measured.
Yeah.
So we can either make up a unicorn fart force that accelerates everything together, or we can go with the actual measurement of force, and that's the acceleration up with an accelerometer.
Right. And we're not the ones that made up the unicorn farts. That was all Alan. We'll hear that in a minute. But I'm like, wait a
Yes,
second. How can you
I jumped
compare?
the gun.
It's okay. But is there more stuff on this video or is this pretty much good and we should move on?
I think that's it. Is there any?
There's like
Oh, you
another
can.
minute or 30 seconds or something left. So
Yeah,
I don't know.
I don't know what
Once
else
it
to
hit
say, but
gravity, I was like, all right, we can stop this shit right now and nip it in the bud. But I think it's pretty much described for people to understand what proper acceleration is. And we'll go back to Bendy space-time guy here. Or I mean, ether
right.
guy.
Great
And
part two.
I sorry.
No,
I
you're
was
good.
just
Go
gonna
ahead.
say, yeah, I will grant them that there. It's possible that there is this, gravitational force that accelerates everything equally. But until it can be demonstrated in any other way other than gravity or bendy spacetime or ether or electrostatics, if any of that could be demonstrated to equally accelerate all states of matter, with no displacement, then I don't believe in it. You got to demonstration is king. You got to show me that.
Word. I agree 100%. Demonstration is king.
Physics, measurements, and predictions with no causal mechanism, and the secondly, predictions of future motion based on actual forces. Okay.
So there's just the definitions, which we all know by now. Don't need to keep repeating. Explained
Now,
it enough, right?
what
Right.
you're
Yeah.
doing
That's
when
good.
you drop a water bottle with liquids in it in an air bubble, or when you are moving it horizontally, etc., and you're disturbing the density gradient, you're doing kinematics. Okay.
So once again, kinematics, describing motion. Dynamics, why the motion occurs.
Right. Except he's ignoring that there is a force measured whenever the water bottle is an accelerometer. Whenever it's got water and air in it, that's two
Yeah.
states of matter. In any other instance of acceleration, those will displace. But whenever they're in free fall, they do not displace, meaning there is no proper acceleration. So it is an actual dynamic interpretation of the motions.
Yep. And when a water bottle is just sitting on the ground, it's in acceleration. Otherwise, the water wouldn't be, or the air wouldn't be at the top of
Yeah,
the
they wouldn't
bottle.
be separated. Yeah, exactly. They wouldn't be in a density. A density. He brings up density layers. The density layers are because of the upward acceleration. That's the
Yeah.
only way. That's what causes buoyancy. That's the only way to cause buoyancy.
Yep.
And is with an acceleration of a container.
Well, that
Or
also debunks the constant too, because that was the claim with going into the constant versus accelerating. If it was constant, then it wouldn't show an acceleration
right,
with
there'd be
the
no net forces observed or measured.
yeah. And like when like the flame demonstration when if there was no acceleration, then the flame would be making a ball. It wouldn't be dragging up the way that it is.
Right.
Like, you know what I mean? It's hard to explain without having the visual,
Right.
but
The flame being less dense and more buoyant than the air around it, so that's why it stretches up,
yeah,
pushes up. Right.
got it. Okay, we'll keep going here.
So in kinematics, relative motion is always true. What that means is if you take the example, observer on the side of the road, a car coming towards the observer, in kinematics, you can say that the car is accelerating towards the observer, or you could say that the observer is moving towards the stationary car. Now, obviously, when you apply dynamic forces to that analysis, you can quickly tell that the stationary observer isn't moving towards the car, right? It's not an equivalent in the forces. So you would have to introduce pseudo forces to make the stationary frame have the equivalent of the moving frame, right? But that's it's obviously not the case. So you can tell right away in that analysis which frame is stationary and which frame is moving. Now, in the case of what's being done with stratification of
What happened?
Right. No, I was just going to say he's exactly right in the instance that in the the horizontal frame that he's describing with the car and the person on the side of the road, like, totally ignoring the frame that we're in, that we have weight, that we are being we would not have weight if we were not in motion accelerating. Like the motion and acceleration is what gives us our orientation.
100%.
liquids and dropping things and moving things in a van All of those things make the same prediction that would be made for a stationary Earth with a downward vector provided by electrostatics or ether or unicorn farts. It literally doesn't matter.
There's a unicorn fart. Sorry. Okay. It literally doesn't matter. And it's like, wait. So if it doesn't matter, then why are you fighting gravity and saying gravity is so stupid all the time? If it literally doesn't matter and it's equivalent to your ether theory.
Right, that's a great point. Like, he's exactly right because it doesn't matter because they're not taking into account the actual directly measured force. They're just making up
Exactly.
a force, and they can make it say whatever they want because they're ignoring the actual force.
Yeah. It's like the controlled opposition of gravity is ether.
Right. Yeah, exactly. So nobody looks at the upward acceleration.
Exactly.
They get them
The other
fighting,
thing,
and hey, look over here. The was
Yeah.
it the Hegelian dialectic or whatever?
Yeah. We figured it out. We have the answer for you. It's just, ether. Here we go.
Right. That's why and then that's why Einstein made the equivalence principle in the beginning because locally, like you can't, and they say locally, so that things in outer space don't apply to it, or things in a far away, not locally to you, don't apply to the equivalence principle. But that's where things can be fudged and measurements cannot be verified. So they
Yeah.
have to, whatever what anybody can verify for themselves, they have to like put into their theory to like cover up their BS in the
Yeah.
as
They
a
have to
whole.
they have to have something for everything. And yeah, I mean, make up your own mind, but this is everyone keeps saying like why are you pushing this? And I'm like, dude, because this is measurable. This demonstration is king. Like that's what this is.
Right.
We
The
should be
upward
covering this.
right, and the upward accelerating Earth is the biggest death blow to the globe model. Like,
100%.
and yeah, and they recognize that they had to put it in general relativity because as the equivalence principle because they know it's there, it's measurable, but they have to act like that. But it's the number one killer for the globe.
It is. Yeah, we don't. If you notice on like any of my other videos with Witsit or with whatever, like there's a bunch of Globers talking shit. But on all these videos with you, like there might be one or two, but in the comments, if you read down the comments, like they don't have responses when we come back at them. Like they can't explain why things in free fall have no measurement on them. Like they can't explain how when you put an accelerometer on the ground, it's moving up. Their own scientific whatever experiments or demonstrations like can't you can't just explain it away. Like it literally is the death blow, and the globe can't exist without it expanding. So the globe would have to be constant. If the Earth was moving, if they admitted Earth was moving up, then they would have to admit that the globe is constantly expanding, which they can't admit that because their Lord and Saviors, NASA, and all them haven't told them that yet.
Right.
So
They've got to set our value and they can't let that go.
exactly, exactly.
thing we have is the acceleration that's measured, right?
Oh yeah. So we basically kind of covered what we needed to on that, right? Kind of
Yeah.
before.
I want to go over. Perfect. You have this video. I wanted to show this video is a great demonstration of an accelerometer, and being that the acceleration measured by accelerometers is not an arbitrary calibration fixed into the device to show an upward acceleration when sitting on the ground. It's an actual true measurement. And I think this video shows it really well.
Yeah.
I've loaded my phone with an accelerometer app and attached it to a camera. Here are the axes of this setup, X, Y, and Z. When I accelerate the system in the positive direction along an axis, I get a positive acceleration reading in that direction. Sitting on a surface, it says that it's accelerating at 1 g, 9.8 meters per second squared. Yet, unlike a car speeding up, it isn't going anywhere. Now let's see what happens when I drop it. It registers 0 acceleration as it's falling. Newton's second law of motion says that force equals mass times acceleration. So, if the acceleration measurement is 0, then any measurable forces acting on the phone must also be 0. Gravity must not be a force that causes the phone to fall to the floor. Now let's show that the acceleration of gravity is upwards, not downwards. If we simply lift the phone, the reading is always greater, not less than 1 g. Upward linear acceleration is in the same direction as gravitational acceleration. Well, maybe you're thinking that the calibration is arbitrary, and accelerometers could just as easily be calibrated to show gravity as a downward pulling force. But here's mine on a rotating wheel. It's correctly registering a centripetal acceleration in the positive x direction toward the center.
Okay.
Right. And if the accelerometer was arbitrary, then it would not be registering the acceleration in the correct direction, on that wheel, showing the inward direction to that wheel, showing the direction of the force.
Exactly. Exactly. And you can do this yourself. Like I actually did this by accident when I first started getting into this, and I was doing Lyft and was trying to talk to somebody at Lyft, and I was in my kitchen and I had it just sitting on my counter, just flat. And you know how when you're driving, it doesn't let you type. It was like, oh, while the car's moving, you can't be typing. And I'm like, I'm not moving. I'm literally in my kitchen and it's on my counter. And then when I picked the phone up and like rested it up against something so it was up and down, then I could type. And I'm like, what the fuck? And I just kept going back and forth with it. I'm like, every time I put it down, it's reading like that I'm moving and it won't let me type. This is so crazy. And like, sure enough, this is, like it, and I mean, you could use like people say, oh, you could program accelerometers. Well, no, like the inside of an accelerometer is just springs. Like there are what's it called? Not manual, but like analog.
Analog, and there's different types that use like electrical capacitance or whatever, but it's all measuring displacement,
Yeah.
inside.
Yeah,
And
so I
so
mean, for those people that claim, oh, it's programmed into it, okay, get an analog accelerometer and test it then and see and up against a digital one and see if they're accurate. Like shit, maybe that's something we should do. Like look on eBay for some old like analog accelerometer or something. I mean, I guess a water bottle is really like an analog
yeah, it
accelerometer.
is.
But I mean, for as far as like actual mechanism with springs and all that stuff, like it's not obviously your phone accelerometer app is like it's not the analog version, but like to claim that all of them are like that when it's not, it's like maybe you need to look into accelerometers a bit more for people that make that claim.
Right.
But yeah, we'll keep moving here.
Matter. The only thing we have is the acceleration that's measured, right? So the way that you analyze that, we have a downward vector, and when we have objects that are experiencing resistance to that vector, right? Stratification inside of a bottle, for example, so like a density layer bottle or a density tower bottle is going to be orientated a certain way, where the heaviest stuff is at the bottom and the lightest stuff is at the top. Now, when that bottle is on your desk, it's experiencing that downward vector, so it's going to be sorted in that orientation. When you drop that bottle, when you pick up that bottle and drop it, that bottle is now moving with the vector. It's not experiencing any net force on it, so it's going to invert stratification in the direction of motion. Now, what you can take that as is, oh, well, that must mean the causal mechanism for the original stratification was upward acceleration. And that's a valid hypothesis. It's not it's not something that you can hand wave dismiss off of what's being presented.
Yeah. Right. And he's saying it's valid because and it's the only way that you can interpret it if you interpret any other acceleration in any other vector as doing that. He says that the density layers are caused by the vector pushing down and sorting the layers of the stratification layers in the bottle. But no, if you accelerate something in a certain direction, the density layers orientate exactly in the same way as in the direction of the acceleration. And so when a water bottle is sitting on the ground, the water separates as the acceleration is going up. If you accelerate a bottle of water to the right, the water goes to the back. It shows you the direction of the acceleration.
Exactly.
Which I know that we keep reiterating it, but it's like I don't see how people don't see it. I don't know.
Right.
To do that, and if you tried to do that, it would only make it seem more valid to the person who presented it. Just a heads up, because you're not providing any substance, you're not refuting the measurement, right? But on the inverse, there's a direct equivalent. So when you're experiencing vector subtraction, when you're moving with the vector, the stratification will flip in the direction of motion. The same prediction is made when you're moving orthogonal to the vector. So when you do an experiment where or a measurement, but it doesn't matter what you want to call it, it's all measurements. When you do that horizontally, you're going orthogonal to that vector, and the stratification will again be displaced in the direction of motion. So we all make the same prediction, but the assertion here is the causal mechanism, right? Because all we're measuring is the effect, the acceleration, right? We don't know what's causing it.
Yeah. Should I play this frame of reference one or the other one, the black and white one that was really cool?
What is this one?
This one is it's pretty short. I'll just play it here. Oh, maybe this is just a screenshot I took, frame of reference.
Acceleration, right? We don't know what's causing it.
We don't know what's causing it. At least we could admit that.
Right. The force that's causing the Earth to accelerate up? I don't know what that is either. I can't say that I know what that is, but I do know that we do have a direct measurement of force.
Yeah, but there is a force. Like their force isn't
measured. It's optically measured. It's not physically measured, directly measured.
Yeah. But here,
when we go into a non-inertial frame, like the frame of the accelerated cart, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it. So we make up a fiction that there is a force. And sometimes we call this a fictitious force. Fictitious forces arise in accelerated frames of reference. The frame is accelerated in this direction, so you in the frame see an acceleration of the ball in this direction, and you say that there is a force causing it. These weights will fall and give the cart a constant acceleration. I'll put the ball up, and then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released from the fixed camera. Ready? I don't know whether you saw that or not, but the path of the ball was the same as it was before, only this time it landed in a different spot. This is because the car kept on accelerating in this direction as the ball was falling. Now I'm going to let you see it again with the slow motion camera fixed onto the cart. This time you saw the ball moving off to one side and not following down the vertical reference line as it did in the constant velocity case. Now suppose you were in this accelerated frame of reference. How could you explain this motion? When we go into a non-inertial frame, like the frame of the accelerated cart, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it. So we make up a fiction that there is a force. So we make up a fiction that there is a force. So we make up a fiction.
That's perfect.
Right. And I did turn that sideways just to demonstrate the upward acceleration.
No, that's perfect. That's awesome. And this whole video is really good. You're going to post the whole thing or parts of it, the parts that were like...
yeah, I have a section of it's like 20 minutes long. I think the whole thing is like an hour with a bunch of different reference frames. But the one that I thought was, pertinent to what we're talking about is like 20 minutes long. And I'm going to post it on my channel. It's like from 1960 from Harvard or something, some university.
Yeah, I'll post your link to your channel in the description again too, because I mean I can't like I go through your videos anytime I have any questions or any like clips that I'm like, I bet you Jason's posted it. Let me go look. And like, sure enough, it's like, and it's all broken down, like short and sweet videos, just breaking down exactly, what we're talking about. And it's like well organized and, a lot of information. So, it all just depends on what perspective you're looking at it through. You know what I mean? Like, yeah, there, a lot of them are, normie, science stuff, but we have to, just like with NASA, we have to take their information and look at it. Like, when I first started debunking NASA stuff, like I'm looking at NASA's website, I'm looking at NASA's videos, like breaking down their, like looking at it through different eyes of a skeptic instead of just a fanboy, So it's the same thing with these science videos where like, yeah, they're making actual measurements, they're making valid points, but they're seeing it and describing it away with this fictitious force, gravity, versus us looking at what they're saying and going, wow, this can perfectly explain upward acceleration also.
Correct.
All right.
Now, the Royal Society got together with Cavendish, and they were like, "Oh, you know what? These balls are oscillating when we have them hung from a torsion wire, and if we take that angle in conjunction with the mass, we can figure out how much force is being applied, and we could say that that's big G, and we can assert that as the causal mechanism for little g."
Cavendish's unicorn farts also.
Right.
Um, did you want to touch on
We
that at
can
all, or just keep going?
Keep going. I want to stop here in a minute after.
Okay.
insert that as the causal mechanism for little g. But all they did was use the mass of the spheres, which already inherently in it has little g baked in, right, for a downward acceleration, because that's all they're accounting for. It's just an acceleration, which you can derive with height, time of drop, how long it takes to hit the ground, and you're basically good to go. That's literally all it is. All they're doing is making a ratio based off of the 9.8 meters per second squared acceleration, right? That's all they did. There's no additional validity to it, right? And then they just asserted that that was the causal mechanism forever. But then that was experimentally falsified through Airy's failure and Michelson-Morley, et cetera, right? Where they went to go measure the velocity that was supposed to be produced by those forces, and they didn't get the numbers that they had expected, which shows that the dynamic cause of what they're asserting, right, mass attracting mass, doesn't work. So in the same respect here, we're in the Earth system. We can't get outside of it to verify either one of these claims. So
Yeah, and I can go ahead and state right here if you want to pause it that
Okay.
what Alan does here, and what a lot of people that look at this claim of upward acceleration do, and I think it's designed this way, is that they automatically put us in the camp of relativity as far as
presenting kinematics.
celestial bodies in motion and like relative motion from us to these bodies in the sky. And he says, he'll say it here in a minute, but he's like automatically puts us in a camp of the motion that we measure on the ground, the acceleration down, has to be the same as what we measure or what we visually see celestial bodies do in the sky. And that's what gravity does, what theory of relativity does. All of that correlates the downward acceleration we measure with rotations in the sky, and we don't we know all we measure is why things fall, and that's what we're going off of. And they try to
Straw man.
strawman us by like putting us in the camp of the globe model and say, well, if you believe this and relativity, then you believe all these motions in the sky. But then if you add these forces, these dynamic forces in the sky, then you'll see that that's not correct either. But we don't know what's in the sky. We don't have any like physical direct measurements of acceleration or forces in the sky. We don't know what the objects in the sky are. All we can use them for is kinematics, and just for periodicity of events. But that's all. I mean, it's just
I used to call them
cycles.
yeah, I used to call them sky worshippers, and it's the same thing that the TFE people did to us. Is like, oh, you don't think this is real? This proves like, no, dude, that even if that was real footage, it still doesn't prove the ground you're walking on. It still doesn't prove like just because there's two different systems, like in our body, there's multiple systems all connected. They don't all work the same way. They don't all do the same thing because your kidneys do one thing doesn't mean that that's how your brain works, or that's how your like same thing with like in a car, like in a when you're working on vehicles and stuff, like there's all these different systems that go into one vehicle, but all the systems do different things and operate different ways, and some of them go around in circles, and some of them go up and down, and some of them do, what I mean? Like you can't say, oh, because this system does this thing, therefore this other system does this other. It's a total straw man argument, and it's bullshit that he always tries to say, or that everybody really that goes against Upward tries to say that we're just like the Globers, when really like Ether is just like the Globers. Like saying correlating and saying, oh well, the sky tells us this and that about the ground, like that's bullshit.
Right.
All right,
Exactly. Yeah.
And you take the position that the Earth is upward accelerating, your position is entirely valid. If you want to get into further analysis of the system and get into dynamics and whatnot, well, you're going to find out that you're going to need an inertial frame to start doing that, right? And I've heard some of the rhetoric for the upward acceleration is that we're not in an inertial frame, that the Earth is a non-inertial frame. That's not true. You can go back to Newton's bucket 200-300 years ago now. These people still haven't figured out Newton's bucket, right?
So Newton's bucket is a thought experiment that was designed to demonstrate that true rotational motion cannot be defined as the relative motion of the body with respect to the immediately surrounding bodies. It is one of the 5 arguments from the properties. Oops, sorry. Properties, causes, and effects of true motion and rest that supports. Okay, that's all. Let's see.
Right. It's basically
There we go.
like drawing a relative motions from the Earth to celestial bodies, and that's what he's doing. He's trying to correlate the Earth to the relative motions in the sky. We don't care about the motions in the sky. They do not have anything to do, or they may not have anything to do with the upward acceleration. We don't don't claim anything about the bodies in the sky.
Sure.
So yeah, we don't have any dynamic force measurements of anything in the sky. All we have is things moving in the sky.
Yeah, and for somebody who claims to be a flat earther and be like, "Oh, space is fake and gay," to even make that claim and to be like, "Oh, yours is invalid because of the things in the sky that you don't believe in, that you talk shit about." Cool story, bro.
Right. That, just like they make up the bendy space time and they make up the the potential causal effects of like ether, unicorn farts, or whatever. They're making up these forces. There's no direct measurement of any of these forces. It's just an explanation to why it could happen. It's not. There's
There's no
nothing
proof.
substantial about it. Right. There's
Yeah,
no proof.
I agree 100%. And really, he's just showing us like the further that we go, the more that they expose themselves. And, absolute space and time is a concept in physics and philosophy about properties of the universe. So, yeah, he talks about space like it's real and like it's something. I mean,
Right.
obviously, we can look up and see, that there's
Yeah.
stuff up there,
It's
but
stuff that
that's
can be visually interpreted by
interpreted. I
anybody.
like that.
Yeah, interpreted by anybody. Like nobody can physically prove anything in the sky.
Yeah.
So where do the laws of physics apply? Well, they apply where they were derived, here on Earth. The lab frame, stationary frame, always makes the correct prediction for the laws of physics. If you're in a rotating frame, i.e. the rotating bucket, and you think you're stationary and the world's moving around you, you will make the wrong prediction for the convexity of the water in the bucket based on your motion, because your motion will be zero in your frame. Everything's moving around you. But yet the water is bending. You'd have to introduce centripetal forces and pseudo forces to bend that water for you. So actually, I think the centrifugal would be bending it in the rotating frame.
See how
You
he
would have to
automatically,
introduce.
if we're moving up, then we have to take into account rotational forces. No,
Yeah.
we don't.
We
Why
don't
are
have to
you
take into
correlating
account.
us
Yeah.
to correlate us to Newton's bucket? We're not claiming any relative motion to the sky. The sky, for all we know, we're a disk accelerating up with a dome over us, and the dome is rotating.
Yeah.
That wouldn't change any of the measurements, the
Well,
optical measurements.
and this video was recorded before Dell started pushing his centrifuge Earth, which is where I think personally Dell got that idea from, was from Alan. Because like I know that they've had conversations and it's been respectful, and like pretty much out of all of the people, like like Dell's talked to what's his name, to Jaren, to Witsit, and it's always turned into a shit show with them. But like with the space audits or the Ether guys, I feel like that was the only conversation that I've heard Dell in where he didn't just fly off the handle at them, because they were showing him respect. They weren't going off
Right.
on him either, the way that like the way Witsit and Jaren like to belittle people and talk down on them. Like they weren't doing that. So I had respect for them. I mean, I still have respect for them. I don't think that like, I don't agree with them, but I don't like, I
Yeah,
don't
I mean, they
agree.
do great research on everything they do. I disagree with them about this, and it doesn't
Yeah.
mean we have to be enemies or anything. But
Yeah. And I mean, like even with Witsit and Jaren, like I could care less, enemies, not enemies, whatever label you want to put on shit, like it doesn't matter. But like as far as the stuff that they've pushed, for the most part, like I haven't seen any demonstrations from them, and that's my only like qualm with them, is that they only read from papers, and they only like they're not taking stuff into the real world and correlating their papers to real world stuff. Like even when they covered the not the Michelson Morley, but that the vertical interferometry, he didn't even notice that the lines were going the wrong way on it. He didn't, talk about he just said, "Oh, this just proves that there's a downward ether," or something like that. Like he didn't
right, a
really go
downward,
into it.
right, a preferred direction of light downward.
Yeah. So, but he said ether. He used the words, "Oh, this just proves ether this way too," or whatever. He didn't like, I don't know, like he didn't go into depth on it. He only showed it for like a minute. Didn't even notice that the lines weren't going the right way. Didn't like show the other guy's video and like really break it down. Like, so I don't know. I mean, it just some stuff I think just goes over their head. And I think the whole reason for having a community out here is to, somebody covers something and they miss something. Like it's up to us to check each other on it. It's up to us to be like, hey, not us like me and you, but like us as a community to call each other out on stuff, because everybody sees things differently through different people's eyes. Everybody has different topics that they go into, they do deep dives on, and they bring that to the table. And not one person can't research everything, like, and I think that that's part of what they're trying to do, is break apart communities and keep people from talking to each other and sharing information. And we shouldn't be so like booty hurt every time somebody addresses us. Like back in the day, in the early YouTube days, like that's how people communicated with each other. Is somebody didn't agree with a video, so they'd make a video saying, yeah, I don't agree with this, and it was more constructive versus like let's attack everybody and call them names and then say that all of their information is bullshit. Like no, I don't think that all of their information is bullshit. I think that they talk about a lot of important topics and break stuff down and help people understand things like in a way that nobody else has out here. But I also think that they're not perfect, and there are things that that should be addressed, that should be able to be talked about. And if they can't be talked about, then that's a gatekeeper. Like if nobody wants to address these issues and nobody wants to really go into depth on it, then like okay, then you're just gatekeeping, in my opinion. And that's like weird that you wouldn't want to talk about it, especially if it's like along the same line of whatever, the same topic. If it's like way off topic, I understand trying to ignore it or whatever. But there was like a point that I was getting to and I lost it. Sorry. There was something else I was gonna say. I'll just keep playing it and maybe it'll come back to me. Oh yeah, the Dell thing. So I think that he got this idea from Alan, because he didn't start pushing the centrifuge. And then it's like he didn't, when he started talking about the centrifuge stuff, it's like he didn't really put all that much thought into it. Otherwise, like he would have gotten, first of all, like the motion, the direction of the motion correct, and he didn't. And then I don't know, like now he's claiming that like, oh, I'm not making any claims, I shouldn't have ever, said that or whatever. So I mean, at least like he admits that maybe that wasn't the best. But I don't know where Alan got that we like, have you ever heard anybody else say that before Dell, about the centrifuge Earth? Like Dell was the first, Dell and William, and they both
Well,
came
no, I
out
mean
at the same time.
it's the only other way to get a fictional upward force or force measurement. You know, would be a centrifuge, like the acceleration measurement that we actually directly measure. A centrifuge would give you that measurement.
But he said that the upward people push this, but I hadn't heard anybody talk about the centrifuge until after this video came out. So like down
Well,
the
he didn't
lane,
I don't think Alan was directly trying to push
yeah,
a centrifuge or even reference a centrifuge. I think he's just talking about rotations as far as correlating us to a globe model, because the globe model does, recognize an upward force like in general relativity, but they also say it's a rotation too. So I
here,
think that's all Alan was doing.
let me re-listen to what he said really quick because it sounded like he was claiming that we said some shit that I haven't heard anybody say in upward. So hold on.
Introduce centripetal forces and pseudo forces to bend that
Wait, maybe I need to go a little
the laws
further.
of physics. If you're in a rotating frame, i.e., the rotating bucket,
Maybe it needs to go back a tiny bit more.
Are
Sorry.
you talking about when he's talking about an inertial frame?
Yeah, well that, and then he said, I could have sworn he said like
right?
I've heard.
So where do the laws of physics apply? Well, they apply where they were derived, here on Earth. The lab frame, stationary frame, always makes the correct prediction for the laws of physics. If you're in a rotating frame, i.e. the rotating bucket, and you think you're stationary and the world's moving around you, you will make the wrong prediction for the convexity of the water in the bucket based on your motion, because your motion will be zero in your frame. Everything's moving around you. But yet the water is bending. You'd have to introduce centripetal forces and pseudo forces to bend that water for you. So actually, I think the centrifugal would be bending it in the rotating frame, but you would have to introduce a counter pseudo force to balance that out.
Okay, maybe I didn't rewind it far enough because I swear he said something about from maybe it was from earlier that the I've heard the upward people,
Yeah,
you know.
are claiming a non-inertial frame. That just means a frame that's not accelerating, which
Oh, okay.
if you go by the
Okay,
definitions of inertial and non-inertial frames, which is just a way to measure motions of different reference frames.
got it. So I
But
was confusing. I think I was confusing the non-inertial with the centrifuge idea or the bucket idea because they were like right in a row from each other. So I
right,
don't
but I
know.
don't, and maybe there's a point to make. I don't think that the Earth is an. I think the Earth is a non-inertial reference frame
So
relative to things falling. I do not think that the Earth is a non-inertial reference frame relative to bodies in the sky that are rotating above us. Like they, in my opinion, they're just accelerating up with us. And they're just going in a horizontal, potentially a horizontal. I have no idea what's going on in the sky. What I see is things going across the sky.
Well, and we do believe that it's all enclosed. It would have to be, right? Like it can't
Right.
just be like Earth and then in space, like infinite vacuum of whatever. Like there has to be a barrier, I would think, at some point. Um, but to claim that okay, the sun and the stars, all that stuff is clearly part of our system. It stays with us, you know. In my opinion, like
Right.
to claim that like, oh well, because these do this, therefore you don't know if those stars and everything is moving up or whatever. Nobody's put an accelerometer on a fucking star before. You know what I mean? Like,
Right.
so all we know, all we're going off of is visual. And I get that, like, they're given the agenda to like debunk this. So what better way than their main debunk being, oh, the stars, the this, the that, the non-tangible objects that we can't, that we can't
Yeah,
even really study.
they can point and declare forces on these objects in the sky, and and just make up stories about forces that could be acting on these objects, but there's no measurements of them.
Yeah, exactly. It's fairy tale unicorn farts.
they tell us
It's just imaginary models that could work.
Yeah, exactly.
on Earth that we're experiencing centrifugal acceleration, and that there's a opposing force that creates equilibrium with that called centripetal acceleration, right? Otherwise known as gravity, right? It just magically pops out there to counterbalance it to make our frame appear inertial, right? So if you're an upward accelerating Earther, at the end of the day, when you get into dynamic analysis, your position will be that the Earth is stationary. It doesn't matter that like if you agree with that or not, like when you get into the analysis of the math, you're gonna have to make it that way because that's the only way any predictions of future motion.
The only way that the math works is if you use our math to make the math work. In other words.
That's so funny because they those guys at Ether, like, they do a great job of breaking down the math and like showing where the mathematics is used, but then he's like appealing to it as well.
Right.
Work. So in short, you're in a roundabout way to simulate and emulate the default position that we already have. So yeah, I encourage people to look into kinematics, where people do calculations and they're like, oh look, we must be right because our math's right, but they don't realize that they canceled out the dynamic force of it, and or et cetera, like when you get into planetary bodies and all that kind of stuff. So
The irony.
He even says it
The
when you get into
irony of
planetary.
well, that even the irony of him saying they cancel out the actual forces, like he did with the accelerometer reading.
Let me just rewind that really quick. That's like such a great little clip right there. It's funny.
or et cetera, like when you get into planetary bodies and all that kind of stuff.
Oh,
So
yeah.
anyway, just some food for
Tiny bit more.
don't realize that they canceled out the dynamic force of it, and or et cetera, like when you get into planetary bodies
Like
and all that kind of stuff.
what cancels out the dynamic force? Like his imaginary mathematics cancels out a dynamic force. Like that's basically what he just said.
That's exactly the way he thinks that whenever you get into analysis of systems in the sky, of rotation in the sky, that if you have to cancel out those forces, but he's the one that's canceling out the actual force that's measured on the ground and saying it's
Right.
all just kinematic.
Exactly. That's crazy. I don't know if you wanted to play this AI video too. We were trying to find videos. It was hard to find exactly what we were talking about. So so I say we, but Jason made this.
First up,
Yeah, I just typed in a prompt about telling AI to describe acceleration, proper coordinate, and kinematics and dynamics, just to make a short video, and this is what it came up with.
Yeah. it turned out pretty good.
Proper acceleration. This type of acceleration is absolute or invariant, meaning that no matter who's observing it, everyone will agree on its value. You can think of it as the acceleration that you directly measure with an accelerometer. It's also equal to the coordinate acceleration in an inertial frame, fancy talk for a non-accelerating frame of reference. To put it simply, proper acceleration is the real deal. Now for you math lovers out there, proper acceleration is given by the covariant derivative of the 4 velocity. This is true whether we're talking about Newtonian mechanics or the realms of special and general relativity. Quite the unifying concept, right? Next, let's talk about coordinate acceleration. This is where things get a bit more relative. Coordinate acceleration is the second derivative of position with respect to time. Since position is defined relative to a coordinate system, this kind of acceleration isn't absolute. Different observers might disagree on its value, especially if they're in non-inertial or accelerating frames of reference. So proper acceleration has both a physical and a mathematical definition, making it something you can really measure. Coordinate acceleration, on the other hand, is strictly mathematical and depends on the observer's frame of reference. So what
So like I wanted to just like take that shot with all the little scientists standing around talking and like put like the Ether Discord, like all the pictures from everybody in there or from their little group. Because that's really, I mean, I hate to say it, but that's what the vibe that I get off them is just purely mathematics, like reading papers, not actually doing actual demonstrations or correlating the mathematics to actual real life demonstrations and whatnot, you know. But yeah, I'll keep playing this because I don't remember what.
exactly is a first order force measurement?
Oh yeah, first order force measurement. So that's like, we already went through all of this, but this explains it a little bit better for people who are still trying to wrap their head around the terms that Jason was using.
Well, it's all about measuring force directly. Imagine using a force meter or a calibrated spring scale to see how much force is being applied or exerted. That's first order measurement in action. Now let's connect this to Newton's laws. Remember F equals sine ma? In classical mechanics, force is tied to acceleration, but first order measurements focus on force itself. Forget about those indirect calculations from acceleration. We're talking hands-on, direct observation here. Let's dive into some real-world examples. Picture this, measuring the tension in a rope or the weight of an object with a weighing scale. These are textbook cases of first order force measurements. Simple, right? But there's a twist. In physics, not all systems are
I
first
think
order.
that's about all.
That's about it. Okay. So yeah, I mean, I think that
A first order system depends
sorry,
only on its current.
I accidentally bump it, like barely touch the little pad thing, and it starts playing again. So yeah, the whole first, like, kind of like the demonstration that you did, that would be a first order measurement or whatever, right?
Right. Yeah. An actual force, like measuring an acceleration by force with a spring scale is
Yeah, and you even had a spring, and they told you not to use this. First, they told you you had a digital one. They said, "Oh, you need to use a spring one, spring scale." And so then you went and got a spring scale, and then what did they say that wasn't like?
they just, and I mean, there's some valid critiques of it, but and not being a long enough distance. But um, and another thing that I like, a lot of times we'll talk crap about mathematics and stuff too, but if you can correlate math directly to an experiment like that's tangible, then math is real, in my opinion.
Yeah, of course, math is real if you correlate it to something in reality.
Right.
Like
If
when
it's
you,
just made up stuff in the sky, then
yeah,
that's all it is made up stuff in the sky.
it's a story or whatever.
Right.
And then, same thing with like when William was trying to say that years needed to be, like longer, faster, this, that, whatever. But then also admitted that physics is scalable and that you can scale, like what you did in the 13, was it 13 feet or whatever, the second one?
22 feet.
Oh, 22 feet. Why did I think 13? Maybe the first one was, no, the first one was like 9 feet and the second one was 22 feet. Um, so that's scalable then. You know what I mean? Like there's no, like, I don't understand how, like, so what, you have to go to like a high rise or something for them to be like saying that it's valid? I don't know. It doesn't make
Right.
any sense to me. Um, but yeah, I think we covered everything unless there's anything else that you wanted to add to it or whatever.
No, that's about it. I've got a few videos that I've put together that I haven't released yet, but I'm gonna put out there just kind of explaining some of the concepts and some of the experiments that have been done in the past that actually relativity uses to their advantage to demonstrate the equivalence principle. So those will be coming out soon.
Nice. Can't wait. Awesome. Well, thanks for chatting with me again. It's always very interesting, and I appreciate all the work that you put into all of this stuff. So, yeah, we'll talk again soon.
Awesome. Thanks.
Bye.